Hello and welcome back to Calculus 1 on this crispy Saturday morning. Right, we have 2.3 techniques for computing, solving limits. We already covered two methods. The method of a chart, right, when you calculate those values, is the one that works all the time. It's annoying to compute all of those values, but you are always able to calculate function values, so that's the one that always works. You have to be able to observe the pattern, right, to tell whether the limit approaches a number or not, and so on. And then you look at the graph. That's another way. But some complicated functions have really complicated graphs to draw, so that might not be always available. So in some cases, it's okay to use the graph. Obviously, if you have the graph already, then yeah, use it. But it's not something that we can rely on all the time. So, methods. Number one, chart, table of values. Number two, graph, both of which were in 2.2. Number three, algebra. So we are going to learn in 2.3, which is now, how to solve limits using algebra, meaning factoring, rationalizing, and other algebra stuff. So that's going to be 2.3. And then there will be some special stuff. I'll call it special stuff in chapter 4. I think it's 4.7, 4.7, or 4.8. Actually, I can check real quick. 4.7. So these will be our ways to compute limits, and you will need to know all of these to survive your, not just Calc 1, but to survive Calc 2 and later, because half of your Calculus 2 course, if you're taking one, will be taking limits, especially the ones from 4.7. So limits are going to be used a lot. In Calc 1, we'll use limits. Well, first we'll do just limits problems, and then we'll go use limits to describe continuity, which will be later today. We'll use limits to define derivative, which would be maybe next week or the following week. And then we'll have, after that, we'll have limits to work with integrals as well. So all of that stuff will be based on limits. So now, let's take a look at these basic ideas. So say we have limit x goes to 3 for x squared plus 1 equals to question mark. We have three ways that we are supposed to know now on how to solve this. So last time we said way number one would be the chart, table of values. So we want to go to 3. Our job is to pick 2.9, 2.99, and 2.999. These are the values that are approaching 3 from the left. It's the red side, right? The Juliet, as we said last time. On the other side, we have the values that are approaching for 3.1 closer to 3. And then we compute these values in our trusty calculator, right? So we'll have, let me just see if this is, okay, plus. There we go. Bars, y1. So 2.9 last class gave us 9.41. And then 9 is 9.94. And then 999 is 9.99404. So we see that this side is approaching 10 because the values are climbing towards 10. On the other side, we have 3.1, which is 1061. Then we have 3.01, which is 10.06. And finally, 10.01, which is 10.006. So we see that from this side, it also approaches 10. And I said last time, if it walks like a duck and it quacks like a duck, it's a 10, right? Good. So now, what we see here is that I can use the one-sided limit. We use the red for the approach from the left. So it was limit x approaches 3 minus for x squared plus 1, and that equaled 10 because of this 10 here. And then the blue Romeo, right, is the limit x squared plus 1 as x approaches 3 plus, this is approach from the right, that one also equal to 10. And then, I guess, purple, the theorem from last class, which said that if limit f of x goes to a minus is the same as the limit of f of x when x goes to a plus is equal to L, then overall limit approaching from both sides at the same time of our f of x is that L. So limit x approaches 3 of x squared plus 1 is equal to 10 because the red limit and the blue limit both gave us 10. Now you see that this does not depend on what type of the function you have within the limit. What you are learning now is stuff about limit. So you will solve the problem the same way if the stuff inside was not a polynomial x squared plus 1. The same applies if it's cosine x, if it's e to the 3x, if it's log base 2 of 5x. No matter what function you get to put inside your limit, if you're using table or a chart method, this is the way to do it. So we don't care. Morning. They're beating you 2-1 now. Yeah. So what you have over here, it doesn't matter which function you put there. The process of solving the problem is the same because you are supposed to learn the theorem which works this particular way. So that was our way to find the limit using the chart. Now, number 2. I said number 2. There we go. The next way to do this is to draw a graph. Now, since I already know my values here, I'll draw the graph through the values. Oops. So this would be exactly the graph for our x squared plus 1. I simply connect these dots, which I calculate as I plug in 0, x is equal plus minus 1, plus minus 2, plus minus 3, and so on. So I am trying to approach 3, and we said approach from the left. We would be going up this line, we would be creeping up to 10 from below. If you go the blue side, we go down the line, we go down the line, and we simply read off of the graph that the limit x approaches 3 of x squared plus 1 is equal to 10 because we see it. That's all it is to it. So we see that this approach is translated that way. So now, those are the two approaches we did last time in 2.2, and they're not very efficient. And, well, chart is not efficient at all because you have to compute 6 values and probably drag a lot of decimals. And if you don't have a calculator, then that's completely different level of annoyance to compute. It used to be cool in old times, right? Because that was actually the entertainment. But now, unfortunately, not so much. And then graph. As I said, sometimes you might not be able to graph because it's way too complicated. And graphs suffer from one more thing, and that is precise. How many of you have Square Notebook now? One, right? One person. You're sitting in a math class with a lined notebook. That's an issue of education, right? That was not addressed early enough, so now you don't know any better. And that's what it is. It's simple as that. Look at my grid on the tablet, right? It's square grid. I could have put the line grid, but line grid is terrible for math because you get to draw crooked graphs and not learn. And that's a problem, right? Again, not addressed for years of math that you had so far. Remember, you had 12 years of math already, at least 12 years of math so far. It's not mine after that time, maybe 13 years or 15 years of math by now, to teach you that math should be only done in a squared notebook and nothing else. They had a very simple solution for me as I went to grades 1 through 8. Anytime I would show up with lined paper to class, they kick you out of classroom immediately. There is no debate. They just say, you don't have the proper notebook for the class, go outside, play ball, school is not for you. And it was very simple, right? So graphs are unreliable because no one cared to teach you that you are supposed to do math on a square notebook and have proper graphs so that you can actually read information off of the graph. Now we always have gold nuggets, so that's great, right? I have to have my favorites, so there we go. For the day, okay, don't get caught. So now, these are the two methods we learned, and as I said, one is annoying, the other one is unreliable. So that's why now in 2.3 we learn algebra ways. So let's talk about algebra ways. The ways of the algebra. So this is, as I said earlier, going to introduce algebraic ways of solving limits. We are not going to use graphs and charts and things anymore. We are going to use algebraic manipulation to solve a problem. Now, before we kick in, let's just write what are the ways. So A, plug in. Now, this is dangerous. Be careful. I wrote it in blood, so be careful. B, factoring. C, cancel. D, rationalize. E, other formulas. Because you might have trig question and you can use trig identity or some other formula from algebra that you learned, split the powers, multiply exponents, and things like that. So there are other formulas. What I listed A through D are the most frequent ones. 90 to 95% of your problems in Calc 1, 2, and 3 are going to fall, good morning, in one of these four categories, A, 2, right? And occasionally, right, occasionally, you are going to see something else. So this would be our list of possible things. Now we first have to address plug it in method, and I did write in red, it's dangerous, and you have to be very careful with it. I made it clear last time, and if you still can't remember or recall, go back, watch the lecture. You will see, you will hear me say that 5,000 times. Limits compute y value of the function differently than what precalculus does. Precalculus computes at the value, which is exactly this, while limits compute everywhere else around value, never at the value, and then they infer what the answer would be. So we've seen that. That's exactly what the chart of value does. Computes values before the number, computes the values after the number, and then looks at the trend and says, this is the answer. Now, the trick is that for the most part, when functions are continuous and some other deals, the value of the function that you compute from precalculus is the same as the value of the limit when you compute it using calculus. So in many cases, you can solve the limit by plugging the value in. But then, if you remember the bridge example, there are those cases where you cannot. So, part A, plug in. When can you plug in? Well, you try, and if it works, you're done. Let me give you an example. Problem we just talked about, x squared plus 1 as x goes to 3, is perfect. 3 squared plus 1 equals 10. We got the value 10. We're happy. Just walk away. We're done. Now, is there a case where you cannot do this? The answer is yes. If you go limit x goes to 1 of 1 over x minus 1 is equal to, what happens when you try to plug in 1? You get 1 over 0. This is the case we cannot plug in. So anytime you end up with a 0 in denominator, you are not allowed to plug the value in. Now, you might say, well, what do we do in that case? there is an entire section that deals with problems exclusively of that kind, 4.7. We are going to deal with some now, some. But 4.7 exclusively deals with those situations. So what you should do? Be patient, okay? That's what it is. Stay tuned. So we have a plug-in method, and you are only allowed to use the plug-in method when you get a value on the other side. This is solid, and just move along. So can you use this to find the limit x approaches pi over 3 of tangent squared x? The answer is yes. Right? Because tangent pi over 3 is very good. Yes, you're correct. So you can just square that value and you're done. So you are looking for tangent of pi over 3 everything squared. So you know you can put the square like that, or you can put square on tangent, whatever. So the answer is root 3 squared is 3, and look at that. Non-weird answer. That's a weird answer, right? 1. You can't divide by 0. We got 3. So anytime when this plug-in method provides an answer, you're done, right? Anytime when it gives you something like this, you can't use it. Another time when you cannot use it is when you have piecewise functions. See, if we have f of x defined to be x for all x's less than 0, and then x cubed plus 1 for all x's bigger or equal than 0, and we are asking for the limit of f of x, of this piecewise function, as x goes to 0, you cannot plug in 0 because it's two different pieces. For problems like this, and maybe I should box off this in a special, yeah, I'll do that. So for problems like this, please note that this would be your left and this would be your right. So we have a limit x approaches 0 minus. And then the function that we are considering is x. So now when I plug in, I get 0. Then I have limit x approaches 0 plus. And now I have to use x cubed plus 1. And when I plug in 0, I will get 1. Not the same. Remember the theorem? Theorem says these guys have to be the same in order for overall limit to exist. So now, by that theorem, we have 0 is not the same as 1. Therefore, limit of f of x does not exist as x goes to 0. So this was the theorem from the last class, and I said this is one of the most important theorems of Calculus 1 because it will help you solve the limits that you can't solve otherwise. So now I'm going to put the whole problem in a box because this is one of the ways to deal with piecewise limits. You are not used to piecewise functions. Now when you are expected to know limits of piecewise functions. So now you have this example, and hopefully you'll practice more from the book. So piecewise functions are going to utilize these one-sided limits. Just make sure which one is to the left, which one is to the right of the value you are observing. And we wanted the limit at 0. So you have x to be left of 0 as a function, and x cubed plus 1 was to the right. So when you put these guys together, Right. Now these functions are basic and simple, so you could have drawn the graph as well. I'll show the graph and see that it's the same thing because there is a jump. Here's your open circle x function, y equals x. So it's a 45-degree line coming into the 0 and stopping there because the barrier at 0. After x equals 0, we are picking up at 1 with a closed circle, and we have our cube function. So you see there's a jump here. I said Romeo and Juliet do not meet at the same location because one, in this case, Juliet would be at location y equals 0, and Romeo would be at location y equals 1, which is why they did what they did. If they just studied limits. I know, right? Anyway. So the next part is, so this was the part on plug-in. If you get this, give up the method. You cannot plug in, you cannot claim does not exist or anything like that, because the problems can be crafted to make you make mistake. If you plug in, you get 1 over 0, you claim no limit, but then there is limit. And we'll see those problems as we go along. So don't use plug-in at any time when you have 0 in denominator. Anytime. So what happens if we have 0 in denominator? Well, here is one of those evil problems, right? Oh, I hate that I numbered these over here, A, B, C. I mean, because now that's going to ruin the... whatever. All right. Factoring. Look at this. Limit x approaches to 4 of x squared minus 16 divided by x minus 4. Aren't you tempted to just say, oh, plug it in? If you plug it in, you get 0 over 0. Are we all good? 0 over 0 there? Do we all see that? Yeah. And then aren't you tempted to say, oh, doesn't exist because you can't divide by 0? Well, sometimes when you divide by 0, the answer is 8. On other times, the answer is 3/4 when you divide by 0. Division by 0 is very tricky business. It requires many years of training. Just like in Star Wars before they ruined it with you pick up. It's just easy, not a problem. You don't need to spend a lifetime of training. It's just, a new generation. It's terrible. Anyway. I hope Disney burns to the ground. Like they don't have to be people in there. Just Disney as a. Anyway, so what we have? Plug-in method will not work. Let me write that in blood here. Plug-in method will not work. Because you are going to get 0 divided by 0 and you can't draw any conclusions from it. I just told you sometimes you divide by 0, you get 8. and you don't believe me. That's okay. Let's do math, and you will see the proof, and then it will make sense. So you say, okay, I can't plug in. What should I do? Then you look at the title. It ruins everything. So, right, you go and say, okay, fine. Let me factor because I know algebra. So you go up there, you say x plus 4, x minus 4, and then denominator is x minus 4. Oh! It cancels. Right? It cancels. So now I have limit of x plus 4 as x goes to 4. Hold on, I can plug in here, right? Yeah, I can. Great. What's 4 plus 4? It's 8. Wow, wasn't this 0 divided by 0? Here you go. See? 0 divided by 0 is 8, if anyone ever asks you. Right? You go out to dinner, it comes up, right? Oh, the other day I was, going about my business, 0 divided by 0 pops up. It's like, yeah, I know, it's 8, right? Bear my calculus class. So, we see that the limit for this function is equal to 8. Now what I'm going to do is I'm going to use the graph to verify that. Is it Desmos? Yeah. Okay. Beautiful free math. Yes. Start graphing. Sure. Oh, maybe you want to see what I'm doing. So I went to Desmos.com, and now I'm going to open parenthesis x squared minus 16 close parenthesis divided by x minus 4. Cool! We got a linear line. Wait, that's a linear line? Yes, it is. Remember what happened when we canceled? What was the function that you had once we canceled that x minus 4 on top and bottom? The remaining was x plus 4. Isn't that just y equals x plus 4? It's a linear line with a slope 1 going with the y-intercept at 4. It's a square grid, right? And you can see number 4 right there. Now, oh, poor Desmos. You are not doing well. Okay, not too good, because as I am zooming in over here at 4, I'm not seeing an open circle. Desmos is not doing too hot in this case. Let's see if we can get Wolfram Alpha to give us better results. We need an open circle at 4, 8. Graph x squared minus 16 divided by x minus 4. Okay, how are you doing? Large? Ah, great, I have to buy the version. Is it? No. Yes. We'll do this one more time using the full Mathematica software, hoping to see good results. Thank you. Divide x minus 4 Perfect. Okay, now we should be able to nope. Still solid. All right, well, the last resort. TI 83s, 84s, anyone? You have a proper phone, you can actually install it for free, just like I did. If you have Apple version, not made for it. Let's graph this in your TI 8384. You will see a missing pixel. That's what's important. I need that open circle at 4.8 because the denominator is forcing that value to be missing. And it's still a linear line. So if you go to functions y equal, you open parenthesis, go x squared minus 16, close parenthesis, divide, open parenthesis, x minus 4. And then you hit graph. And then you go window, x min negative, no, x min 3, x max 5, and then y minimum 7, y maximum 9, because I want this to be in the center of my screen. And I hit graph. I'll just go around. Do you see right in the middle? Missing the pixel? Mm-hmm. Missing pixel? Yeah. Yeah. All right. Those of you with calculators, so see that there's missing pixel in the middle. There's no dot in the middle of the screen. That's where the value 4.8 is. Okay. And 1 minute calculator. Okay. So now, what do we have? We have all right. So what we have there is, you saw it on a graph. It's a linear graph because this function does cancel to a linear function. And this linear function will have an open circle at 4.8 because that's where the denominator was 4, right? Was 0 at 4. And it could not have a value. So now, if you were to plug in a value, you would have 0 divided by 0, and right, you might claim, oh, limit doesn't exist because we are dividing by 0. Lies, right? In this case, 0 divided by 0 equaled 8, right? All I need to do is to change the function a bit, and the limit would be different value. Say, x squared minus 25 divided by x minus 5. You still 0 divided by 0, but this time it gives you answer 10. So, you can make this be technically anything. Division by 0 is very tricky business. So, some of the problems, as you can see, we can solve by factoring and then canceling. Right? We cancel x minus 4, and then we get to the problem that we can solve by plug-in. Right? So this part of the problem was solved by plug-in because when you plug in 4, there was no division by 0, nothing weird, it was just straight through and you're done. All right, let's take a look at the problem. I'm really regretting that I that I started teaching this way, this lecture with A, B, C, D, and then writing these subtitles. It ruins the flow, but it is what it is. How about square root of x minus 9? No, square root of x minus 3 divided by x minus 9, let's say. As x goes to 9, I did pick the worst possible value. What's the square root of 9? 3. Thank you. I know it's calculus. So 3 minus 3 in the numerator is 0, and 9 minus 9 in the denominator is 0, and that kills our plug-in method, right? Immediately. Great. And then you say, oh, I can't plug in. What should I do? You look at the title. Oh, okay, right? Because there will be titles when you have your exam. There will be titles. Exactly. No, right? You need to know what to do. So what are we going to do now? Well, the title says rationalizing. All right, let's rationalize. What does it mean, rationalize? It means change irrational expression into a rational expression. Rationalize. So, we multiply by a conjugate. We change the sign. And then grind through algebra. So all of these are basic algebra skills. I think intermediate algebra was the one. So we have x times root x, that's x. The middle terms will cancel because you have minus 3 root x and plus 3 root x. And then you have minus 9. And because I am experienced, I am not going to multiply on the bottom. I'm just going to leave it in the denominator. So now these guys cancel. And what you are left with is limit x goes to 9. You have x minus 9 here. And you have x minus 9 in the denominator. You see, I didn't multiply. It's called experience. So now these cancel. And you are left with limit x goes to 9 of 1 over square root of x plus 3. And if you plug in 9 now, you get 1 over 6. Now you can plug in because you're not going to get 0 in the denominator. Well, this time we divided 0 by 0 and we got 1 over 6. That's cool. So that's yet another algebraic way for us to solve these problems. Now, there is a way to do this problem, like really cool way to do this problem. Let's go green. Haven't used green much. You get to do this only if you're like a math gangster or something. Look at this. Limit root x minus 3 divided by x minus 9 as x goes to 9. Ready? Should I had my sunglasses on. Instead of rationalizing, I factor. Root x minus 3, denominator factors into root x minus 3. Root x plus 3. I know, right? You have never factored anything like that before. But you can write x as a square root of x squared. Square root of x times square root of x is x. And then obviously 9 is 3 times 3. So you can use the good old a squared minus b squared is a minus b, a plus b. You can use that formula on anything. It doesn't have to be just x squared minus 100 and then you can use it. You can use it on anything. Just as a side note. So if you want to factor x minus 5, it will factor into root x minus root 5 times root x plus root 5. That was not mentioned in your algebra class ever, but you can do it. So you can factor anything. If there is a plus there, you get complex values on the other side. You just get i's on each one of those root 5. That's it. All right, so now, going back to the problem up there, I get to cancel these, and in the next step, I immediately have 1 over 6. Much faster. I don't have to foil, I don't have to multiply, I don't have to do any of that stuff. So quickly, right, factor that. Now, as I said, this is the next level. So if you know rationalizing and you are able to grind through it in a reasonable amount of time, you don't have to worry about this. So those would be other techniques. What is the limit as x goes to pi over 3 for secant squared x? It's going to come up eventually in our class, and you might want to know how to do this. Well, we can use trig identities to solve this. I will do this problem in 2 different ways, and then you pick your favorite, right? So the standard way would be to transform, because we generally don't know the values of secant, cotangent, and secant, cosecant, and cotangent. Generally, we don't know those. Well, generally, people don't know any values, but these are even worse, right? So I'm going to change secant into a cosine, and this becomes 1 over cosine x squared as x goes to pi over 3. So what's cosine of pi over 3? Very good. So the answer is 4. So we can do this by using this identity, or we can use Pythagorean identity as well. Let's go blue. Or can say limit x goes to pi over 3 for secant squared x. Use Pythagorean identity. This is also your Precalc 2, so you should know this. 1 plus tangent squared x. So now we get limit x goes to pi over 3 of 1 plus, and I'll put tangent x squared. So this is, when I plug in pi over 3, it becomes 1 plus tangent of pi over 3 squared, which is 1 plus root 3 squared, which is 1 plus 3, which is 4. Obviously, you have to get the same answer either way you do this problem. So in some cases, you will be using trigonometric identities And that was that part T or whatever I numbered it up there in the list. So to solve limits, chart or table is always going to work. For every single problem you ever write down, chart is going to work. Except it's annoying to calculate all of those values, drag the calculator with you, carry those decimals, look at the pattern, doubt yourself with infinities. We'll get there later. So it's not a method that you really want to do. The same like graphing. You either know the basic graphs from pre-calc, or you have to compute the points every time and then connect the dots. You learned that in middle school, right? To compute values and connect the dots. That is the method of graphing that works on 100% of functions. It's just annoying to do because you want to assign x values, compute the y values, hope you compute the right y values, because if you didn't compute the right y values, then you will miss the important part of the graph, right? Where's the x squared important? At the bend. It's not important, far away to the left or the right. No one cares about that, right? Or any of the functions. X cubed has that squiggle. It's important around the squiggle. If you don't know what a squiggle is, right? If the function has shifts left, right, and so on, and you just compute from -2 to +2, you're going to miss important stuff. So that method of graphing is not that great. The same token, it's not great to compute the chart every time because it's annoying. So we want to know some of this algebra to grind through these problems as they come up. And as I mentioned, right, half of your Calculus 2, half of that course is taking limits. You're not learning limits there, you're just using them in every single problem. So there will be about 2.5 chapters of Calc 2 are using limits exclusively in every problem. So you need to know this very well. Great. Let's take a look at some homework exercises from the textbook and be done with this section. Homework. Oh, I forgot to list limit laws. Sheesh. These will come in handy later, and there are some homework exercises for it. It's just limit laws. So number 1, sum. Limit of f of x plus g of x is limit of f of x plus limit of g of x. So you do them separately. All of these limits are x goes to a, so I'm just not going to write it, but they're all x goes to some value, right, a. 2. Difference. Same thing. Limit f minus g is limit of f of x minus limit of g of x. Three, constant multiple. Which is limit of CF, so that's a constant times a function. You can keep constant outside, just worry about limit of f of x and then multiply by constant later. 4, product. This works only for limits. It will not work for derivatives or integrals later. So if you have limit of a product, you can do the product of limits. Very dangerous rule because it only applies to limits. It does not apply later on in our course. Same thing for quotient division. Limit of the quotient is the quotient of limits. Again, works only here and nowhere else. We have power, meaning limit of f to the n would be the same as figuring out the limit of f of x first and then raising everything to the n later. I actually already used this rule, I haven't told you. It was right here. Right? And root. I'm not sure why is this a separate one, because these are also exponents, right? Third root is 1/3 exponent, power, 1/3. But they have it as a separate one, so whatever. As you can see, it's the same as number 6. Because exponent rule is exponent rule. I don't care if I have an integer or I have a fraction. It's the same rule. If it's an integer, it's exponents. If it's fraction, it's roots. But it's the same concept. So those would be the limit laws. And these limit laws can help you with these cute problems. In the back, they say, let limit x approaches a of f of x be 7. Limit x approaches a of g of x to be 1. And limit h of x as x goes to a to be, let's say, 3. Compute limit x goes to a of f plus 3g divided by h squared. That's in your homework. Now, using the limit laws up there, you take this limit x goes to a of f plus 3g divided by h squared and break this into limit of f plus 3 limit of g divided by limit of h, everything squared. And now you replace the blocks. Limit of f of x equals to 7. So the entire block of limit f of x, which is this block, limit f of x, gets replaced by 7. Plus 3 times, then you have a next block, limit g, which is this, limit g, so it's replaced by 1. Divided by 3 squared. So this is 10/9 at the end. So we calculated the limit to be 10/9, not even knowing what the functions are. We just had the limits at the circle. You're technically just combining y values, right? We talked about limits being fancy way to compute y values. So you just combine the way they are put together. Okay. And now it's time for us to discuss one of the extremely important limits. One very important calculation that was there in Precalc1, which you probably forgot. I know that someone was bothered by it on the homework because I did receive email and I said I'll talk about it in class because it is insanely important. Now, I'm not sure if you can recall the name for the formula because it's been in Precalc1. That was like, what, 17 years ago or something? And I mean, an equivalent in how much you remember from your previous class is equivalent of 17 years ago. I'm not sure if you remember the name of the formula. You were exclusively taught this formula in Precalc1 without knowing what is this for. And you're not going to know what is this for at least for another 2 weeks. But, oh no, actually maybe next week. Yeah, next week you can find out. You'll know next week. No, I'll tell you today, whatever. All right, that's the deal. Does anyone remember the name? So you learned this in chapter 1 in your Precalc1 class when you learn function composition. And they introduced this in the class and said, just learn this, right? And then they gave you 2 or 3 problems to the homework, which you probably ignored. Pretty much sure it wasn't there on the exam. So that's why you don't remember. Without this formula, there's no technology, right? You have to give up everything. Computers, cell phones, everything that has electronics in it, and about 90% of other stuff that was used, that is created by using physics and stuff like that. This turns to be one of the most important formulas of our existence in our technological world. Obviously, before that, it was easy. Bang 2 rocks, make fire, and pray. That's it. But now, we have a little bit more than that. Because of this. So the formula that I'm talking about is called the difference quotient. And it's f of x plus h minus f of x divided by h. So this formula was introduced to you in Precalculus1 course, probably not elaborated on its importance and use later on. And this was introduced to you so you can practice function composition and combining functions together. So combining old functions to make a new function. I believe the section for this would be 1.7 in your chili pepper book that you can find in the tutoring center or library if you don't have access to it now. I think 1.7. So, what is this? Well, the way it's stated over here is nothing. Until you, in 3.1, put the limit in front of this thing. When you put the limit in front of this thing, in 3.1, it becomes a definition for the derivative. Derivative, as we talked earlier, is measuring the change, which is foundation for everything we have today, because everything rests on the shoulder of calculus. All of the physics, all of the engineering, all of the chemistry, all of the, well, not bio yet, but it's coming up. You still have to memorize in biology. So, in all of the sciences where you don't have to memorize, where you can reason, this is where it starts, with the limit, right? So let's talk about computing the difference quotient. And then your homework assignment has a whole bunch of these for you to compute without telling you that you are actually computing the derivative. In 3.1, I get to do the same thing and just put appropriate label to it. In 3.1, we are not going to learn a new calculation. We're going to learn a label and what it means. The calculation will be exactly as you see it right now. And that would be, again, an exam question, a homework question, a lab question, right? You will have this everywhere because it would be the limit definition of the derivative as it is. So let's talk first about difference quotient. So I'm talking pre-calc right now. Here, pre-calc. No limits, no calculus. I want to find, so compute dq, this is difference quotient, not Dairy Queen. Compute dq for f of x equals x squared minus 5. There we go. So what do? We first calculate the piece f of x plus h. This is function composition, which means you will be replacing each x of your function with whatever new function is. So this will be x plus h squared minus 5. The shape, the outer shell, or whatever you want to call it, of these two has to be the same. What's under the square is different. Now, note, x is the same as x plus h is the same as x plus h. I wanted to put orange over here. So when I say shell, what do I mean shell? Shell is you have something squared minus 5. That cannot change. If I was looking for f of a heart, right, because the Single Awareness Day is coming up, there you go. Heart squared minus 5. It doesn't matter. Whatever gets to be in here is what's going to go under the square. So to create this f of x plus h, we are going to replace x by x plus h. And now I have all of the building blocks that I need to compile difference quotient. So difference quotient is equal to, instead of f of x plus h, I have to put, oh, actually, let me expand this. This is going to be x squared plus 2xh plus h squared minus 5 when we expand algebra there. So I have x squared plus 2xh plus h squared minus 5 minus x squared minus 5, that's f of x piece, everything divided by h. Simplify. X squared plus 2xh plus h squared minus 5 minus x squared plus 5 when you distribute that negative. X squared. Why is this not changing colors when I click? X squared and x squared cancel. Positive and negative 5 cancel. And you are left only with terms that have h in it. This is so annoying. There's some lag over here. Because it does click on the black up there, but then it doesn't change it fast enough for me to start writing. 2x age plus age squared over age. This is your checkpoint. After cancellation, the only terms that are allowed to remain are the ones that have age in it. Because the next step is to factor age, and then this age would cancel. And that is crucial for our calculus calculation. And the difference quotient over here is 2x plus age. The limit that eventually will be there will be age goes to 0. That age at the end would die, and you would say that the derivative of x squared is 2x. Some of you might know that already from your previous life experiences, right? You might know that the derivative of x squared is 2x, and this would actually be the proof. And we just did the calculus proof of that. Now, again, I'm not going to define this as a derivative right now because that's for 3.1. Now we are learning mechanics of solving difference quotient. And if there was any justice in the world, right, 100% of you would be expected to know this 30 minutes ago, before I started talking about it, because you learned this in Precalculus 1, right? But there is, do this for 1 over x, square root of x plus 3, right? And all of these other functions that you can think of. Hard ones to do this with would be sine x, e to the x, because they have some of the scary limit laws that you have to use to plow through these. So this was your review of pre-calculus for a difference quotient for the formula that you must know in order to survive the rest of this class and then following classes. Back to calc. Yeah. Calc. Nice. So, homework problem. This is a difference quotient problem. Limit age goes to 0 of 1 over 5 plus age minus 1 over 5 divided by age. It's a difference problem. Your x is equal to 5 in this case. You can do this with replacing 5 by x and doing the general case. So you just need to simplify this, see what happens at the end. Since age goes to 0, your answer at the end better have no age in it. So what do we do? Well, the only thing we can do here is add fractions. Subtract fractions. So common denominator would be 5 times 5 plus age. Cross multiply into 5 minus 5 plus age. Still dividing everything by age. Limit age goes to 0. Now we have on top 5 minus 5 is going to go away, so you have a negative age divided by 5 times 5 plus age divided by age, and I'll put age over 1 so it's easier to deal with the double fraction. You multiply 2 that are far apart and put it upstairs, and then you multiply 2 that are close by and you put it downstairs. So we have negative age divided by 5 age, 5 plus age. So that was the double fraction. A over B over C over D is AD over BC. So now age cancels, and we have a limit age goes to 0 of negative 1 over 5, 5 plus age. And when you plug in age equal to 0, in here you get negative 1 over 25, because 5 times 5, right? Age is 0, so age dies off. I can do that by striking this arrow through and pointing to 0, because limit of age goes to 0. And all you're left with is 5 times 5, so you get negative 1 over 25. And that will be the value of the difference quotient. And next week we will say the slope of the tangent line is negative 1 over 25. For right now, the answer to this completely imaginative and random problem is negative 1 over 25. So this is a full problem for difference quotient, and this is just mechanics, right? Mathematical gymnastics. We can do this. We'll give it a purpose next week. Another really cool problem, sometimes I used to put this on the exam. Sine 2x divided by sine x. I'm gonna go hunt some water. I'll be right back. I solved this. Can we plug in? No, right? 0 over 0. But we all know that the answer is actually 2 in this case, right? We use basic trig identity. Limit 2 sine x cosine x divided by sine x. Sine dies, and we're done. Limit 2 cosine x as x goes to 0. Now we can plug in. Cosine of 0 is 1. 2 times 1 is 2. And this time 0 divided by 0 worked out to be 2. Yay! For calculus. And let's take a look at one of these. This was problem something. What was this problem? This was problem 60. 60. Let's take a look at 65. And then take a break. Says limit t goes to 2 plus of 2t minus 4 divided by t squared minus 4. Yes. All right, let's take a look at this together. So we start by observing we have absolute value function, right? And those could be tricky because we need to know whether we are using 2t minus 4 or negative 2t plus 4 for these values. If you don't recall your pre-calc, absolute value of x is defined to be x for all x's bigger than 0 and negative x for all x's smaller than 0. Right? You can put equal on either one of them. So now, if you have, let's say x is equal to 3, then the answer of absolute of 3 is 3. But if you have x equals negative 3, then that negative 3 will be plugged in here. Negative and negative make a positive, and the answer is 3 again. Now you have this. And you also have the value here. So when you plug in 2, you get 2 times 2 minus 4, which is 0. So this is right at the verge of being either positive or negative, but you have a plus sign. Because you have this plus here, that means that you will be using function as is. So we are looking at the limit t goes to 2 plus of, now you can factor out 2, get t minus 2, and you factor out the denominator, t minus 2, t plus 2. So this is one of those problems where you factor. These guys cancel, and you are left with something that you can quickly substitute in, just plug in, because you have 2 divided by t plus 2. This becomes 2 over 4, which is 1/2, so the limit is 1/2. So absolute value a little bit trickier, but still possible if you know the definition. You have few of these exercises with absolute values to practice. 1, 2, 3, 4, 5, at least 5 in the book, but then there'll be more online. Please try these, and if you run into trouble, then let me know and we'll go from it. All right. That's 2.3. Methods of computing limits using algebra. So we have plug-in, factoring, canceling, rationalizing, and then trig identities. So all of the algebra stuff that you learned in algebra course or pre-calculus course is going to be used here to solve limits. Then you always have the other two fallback methods, graph when possible, and then charts of table of values work all the time, but they're annoying to compute. So in general, we avoid them, use them only if we have to, if nothing else worked. Bye.